Hi guys, welcome to the next lecture. See, in this series of pre-calculus lectures, a very important part that we must recapitulate on is the inverse function. I have been talking about graphs, right? Today, I want to reach to the point where we can discuss the graph of an inverse function. So before that, let's recap the idea of an inverse function. In general, the moment you think about inverse, the word inverse, what comes to your mind is basically the idea of reversal. So, if we start from point A and we're reaching point B, is there a way to go from B to A as well? If there is, that means we're able to reverse, right? So that's the whole idea of an inverse function as well. It describes functions that reverse one another in the sense that each undoes the effects of the other, which basically means that it's a kind of relation that you can reach from left to right or right to left. It's that kind of a relation, okay? Or mathematically, the idea of solving an equation y equals to fx for x as a function of y. So you already have y as a function of x. Mathematically speaking, inverse is the scenario where I'm actually able to get x in terms of y. So I'm able to get x as a function of y. And if this kind of existence is happening, then that basically means that I'm able to reverse, right? For example, suppose we start with a function y equals to x cube plus 1. That is, y actually is equal to some fx, right? Y is a function of x. This can be solved for x as a function of y. You can actually figure out x in terms of y. How I can do that? So basically, from here I know that x cube will be y minus 1. And if I take the cube root of y minus 1, I will get x, which means that I am actually able to get x as a function of y. So we are able to move from here to here and from here to here, back here. We're able to do that. What happens is that, one thing is better in one scenario, one thing is better in another scenario, nothing else. So writing y in terms of x is better. When you have to find y given x, and number 2, which is writing x in terms of y is better when I'm given y and I have to find x. Then I have to find x given y. Okay. How are they related to each other? Y equals to fx and x equals to gy. That is what is very important to understand. This reversal that we are talking about. What is this reversal all about? What is actually happening? So what is happening is that we are saying that x is equal to gy. That means when I will put y as f of x, that is, I will be looking at, so gy will be equal to g of fx. And we are saying that x is equal to this. And we are able to get x. Then this reversal is happening. Then this inversion is happening. So in terms of the formula, so your g is cube root in terms of the function that we had taken as an example. I'm going to carry on that itself. So g of fx is equal to cube root of f of x minus 1. Why? Because fx actually is y. And what do we have? We have that g of y, or we have x is, let me just write down directly, x is, we have figured out that x is equal to cube root of y minus 1. Now y is fx. So therefore, cube root of fx minus 1, right? Cube root of fx minus 1. Now what is fx? Fx is x cube plus 1. So x cube plus 1 minus 1. When you open it up, 1 cancels. And what do you get? You get cube root of x cube, which is what? Which is x itself. So yes, what is happening? G of y is actually turning out to be equal to x. Okay. So that's how y equal to fx and x equals to gy is related to each other. Similarly, we are talking about f of x. So f of x, now what are we saying? We are saying that x is gy. X is gy. F of x is f of gy, that means, right? Now, what is f of any input? F of any input is the cube of the input plus 1. So now the input is gy. So you have gy whole cube plus 1. Now what is gy? We figured it out. What is gy? Gy is cube root of y minus 1. Now whole cube of that plus 1, which means what do you get? You get cube root cube. So that means y minus 1 comes out, plus 1 gives you y. So yes, what's happening? F of x is actually equal to y, and g of y is actually equal to x. So that means this is a scenario where you have an inversion happening. Yes, these are inverse of each other. They cancel the effect of one another, in other words. And when this is happening, you have a special term. In this case, what is that term? The term is inverse. And we write it down as, if f is the function, we write down inverse like this. F inverse, f power superscript minus 1 for inverse. Okay. Please note down, this essentially means what all that we analyzed right now. If f and g satisfy, number 1, g of fx equals to x for all x belonging to the domain of f, and number 2, f of gy is equal to y for all y belonging to the domain of g. So what's happening? G is cancelling the effect of f is cancelling the effect of g. That means that f and g are inverse of each other. Then we say f is an inverse of g and g is an inverse of f, or they both are inverse of each other. Simply saying, we can say that f and g are inverse of each other. So we can give name to g. We can say that g is nothing but, we will give it a symbol of f inverse, which is f superscript minus 1. Please remember, f inverse is not 1 upon f. Please do not ever confuse yourself with that. It doesn't mean 1 upon f. F inverse means that the effect is cancelling of these two functions. Okay. And hence this is happening. G of fx equals to x, f of gx, gy is equal to y. Or in other words, what is happening? F inverse of fx is equal to x, f of f inverse y is equal to y. So that's what we mean by cancelling effects. We even call these two equations cancellation equations actually. So where in our example, we had y equals to fx, that is x cube plus 1, that was number 1, and x is equal to f inverse y, which turned out to be cube root of y minus 1. So that was the inverse function. Now, what is happening here in terms of independent and dependent variable? X is independent in equation number 1. If I quote y equals to fx like this, y is dependent on x and x is independent. In the second equation, what's happening? Second equation is f inverse y. So y is independent and x is dependent. Okay, so that's what is happening. That's what is the reversal, nothing else. In fact, why am I mentioning this here? I'm mentioning this here because when we would be graphing these two functions, we would actually want to graph them together on the xy plane to see what's happening. So we would like to take just one independent variable and one dependent, meaning hereby f and f inverse, these are just functional forms. So you can clearly write down fx as x cube plus 1. That's how we wrote it, right? Then we said f inverse, I can take the input again as x. The functional form is cube root of input minus 1. So you can do that. And when you will do that and graph, you will be able to actually graph on the same xy plane, taking x as independent and y as dependent variable. Okay. That's why I wanted to mention this here. Let me give you a quick recap of domain range when it comes to inverse. So you have a domain of f, you have a range for f. What about f inverse? Remember, we've done this before. So f is a function, say, from a to b. Okay. Now, assuming that b is actually the range for f. Okay. Now, x is an input here. And when you apply the function f, you get y, which is here. If f inverse is there, that means y should be connected to this x here, back here. So when I will apply f inverse y, I should get x, right? That's what it means. So what is happening throughout? If we talk about domain of f inverse, what's happening? The range of f should be the domain for f inverse, and the domain for f becomes the range, right? So domain of f inverse is the range of f, and range of f inverse is the domain of f. Always remember this. That's how you construct an invertible function. And with this domain range analysis, a lot of questions should come to your mind. The first question being, existence. Will f inverse exist every time? Not every time. What was the requirement? Remember? So you have a function f. The inputs are xi's, x1, x2, x3, x4, x5. Suppose x1 is mapped with some y1, x2 with some y2, x3 with some y3. You can interchange also. You can make it y4, y5. You can do all that. But all we are trying to say is that one particular input here, one particular element here is mapped with one particular element here from A to B. Your domain cannot have idle elements. So of course, x1 to x5 all should have an image, and they should have a unique image. And if you have one particular xi mapping up to one particular yj only, so which we call one-to-one correspondence, remember? If you have this one-to-one correspondence, in that scenario, you can talk about going from B to A. And That going from B to A comes with the function, application of the function F inverse. That's what is the criteria for existence of an inverse. So looks like the criteria for existence of an inverse is one-to-one correspondence. Now, please remember that F inverse exists if and only if F is, there is a one-to-one correspondence, which in other words we call bijection. F is bijective. Bijective means it's one-to-one and onto, right? Moreover, if we can define the inverse such that the domain of F inverse is range of F. So please here try to understand. When we started off with functions and we were talking about domain and range, I always mentioned it again and again that whenever it's written F is from A to B, this is your domain, A is your domain, and B is your codomain. It's not really the range. The codomain may be equal to the range or may not be equal to the range. It is not necessary that it is always equal to the range, right? So if it is not equal to the range, that is, the function is not onto. That's what we mean by onto. Onto function or surjective function means that every element in the codomain has a pre-image, which means that range is equal to the codomain. If that is not happening, so does it mean that I cannot have inverse of that particular function? Well, you can still define inverse. How you can define inverse? If you take the invertible function such that you take domain of F inverse as the range of F instead of codomain, then you can construct the inverse function. Okay, please remember this. This is a very important fact actually. So what you need to understand is that we are talking about the domain for F inverse to be range of F. Range of F is F of capital A, that is a set A that tells you range. So in that scenario, you would just require the function to be one-to-one. You can't get rid of one-to-one. One-to-one is required because otherwise it cannot happen. One-to-one is required because think about it. If a function is many-to-one, that means from the input set, say two elements are mapping to one element here. So this is say x1, x2, and it is mapping to some yi. When I go back from B to A, what do I do? One input mapping to two outputs? No, that cannot happen. That will not be a function. So one-to-one is a required property whatsoever. It's the most important thing. So if a function is just one-to-one, then also you can construct inverse by taking the domain of the inverse function as the range of F. Okay. Then I would like to talk about the horizontal line test. Horizontal line test tells you if you can have an inverse or not, because horizontal line test will tell you about one-to-one function. So just like the vertical line test tells you whether the function, it is a function or it's not a function, right? And horizontal line test tells you whether this function is a one-to-one function or not. A function has an inverse function if and only if its graph is cut at most once by the horizontal line, at most once. For example, if you take the graph of, say, x squared. So this is the graph of x squared, y equals to x squared. Now, if I create a horizontal line like this, we just require one counter. So if I create a horizontal line like this, now what's happening? There are many zillion horizontal lines I can create. They will cut this parabola at two places, right? At two places. So the inverse will not exist. Clearly, because this is not a one-to-one function. It's not a one-to-one function. So the complication that I was talking about, if it's a many-to-one function, so you are saying that two x's are going to one particular y. How do I come back? That will not be a function because remember, one to many is not a function. So the inverse function would not exist, right? That's the reason. Now, similarly, if I take the graph of y equals to x cubed, which is this sort of a graph, now if I take horizontal lines, it will cut at most one place. And yes, this is an invertible function because it is a one-to-one function. And hence I can construct an inverse function out of it. Okay, so this is called horizontal line test. Just like you use vertical line test to check whether f is a valid function or not, you use horizontal line test to figure out whether you will have inverse for this particular function or not. You have understood the concept that I've been talking about right now. Then I think you can answer this question, or you can fill this blank. Increasing or decreasing functions are invertible. And the reason is that they are one-to-one functions. So I can create an inverse out of it. They are invertible for a simple reason. See, when you have an increasing function. So let me talk about increasing function. In an increasing function, if x1 is greater than x2, that implies f of x1 is greater than f of x2, which gives you a scenario something like this. So what's going to happen is that distinct inputs will always give you distinct outputs. And well, yes, we're talking about strictly increasing, strictly decreasing here. So since that will happen, that means that it will be a one-to-one function. But the same concept will also go with a decreasing function. Again, strictly decreasing. So if x1 is greater than x2, then that would imply that f of x1 is lesser than f of x2, and that's what is a decreasing function. So it goes something like this. But here also, distinct inputs will provide you distinct outputs, and that's why you will be able to get an inverse, because you know that there is a one-to-one mapping. One-to-one mapping is there, and we will make it a one-to-one correspondence if we take the domain of the inverse function as range of f instead of codomain. Okay, so any increasing, strictly increasing or decreasing function, because it is a one-to-one function, it will be invertible. This is extremely important for us to actually note here. Now, finally, with all this background, we should be able to work up through the graph of an inverse function. So let's work on that graph. Let's explore the relationship between f and f inverse graphically. What we will do here, let's take x as an independent variable for both. First of all, I just spoke about it a few minutes back. It would be good for our representation graphically if we take x as an independent variable for both. The invertible relation is depicted by f inverse, no matter what input you are taking, okay? So y is equal to fx and y is equal to f inverse x. That's how we will represent it on the xy plane. When you have an inverse, what exactly happens? So you have an input A, which we are saying is giving you, when you apply the function f, it gives you f of A, which say is equal to B. Now, since we have an inverse, this B, when we apply f inverse, will give me A. So in this process, what is happening? B is equal to f of A, and A is equal to f inverse of B. That's what is happening, right? So when it's a graph of f, the point on the graph is A comma B or A comma f of A. And when it is the graph of f inverse, it is, the point will be B is your input and f inverse B is what you get as an output. Well, f inverse B is nothing but A and f of A is nothing but B. So what are we looking at? We're looking at on F, we are looking at the point A comma B, and on F inverse, we're looking at the point B comma A. The values of A and B is fixed, okay? So, which basically means let me just write it down once more formally. If AB is a point on F, BA then will be a point on F inverse. That's what I just said. AB is nothing but A comma F of A. BA is nothing but B comma F inverse of B. That is, B is equal to FA and A is equal to F inverse B. Right? So reversing the coordinates of a point on the graph of F produces a point on the graph of F inverse X. What kind of a relation is this geometrically? Let's find it out. Without taking any particular function here, I just want to work with AB and BA and look at geometrically or graphically what is that we're getting. Suppose AB is a point on F. So the graph of F is somewhere here and AB is a point on that. This is the point AB. Suppose AB is basically 7, 2. So A is 7, as you can see here, and B is 2. Okay, as you can see here. This is AB. Now BA will be 2, 7, right? So BA will be, this is 2 and this is 7. So this is BA, where y-axis value is 7 and x-axis value is 2. Now, can you see the lines that I have created here? This line, this line. This is for us to understand what's happening here. And additionally, what I've done here is that you have a line y equals to x here, which is basically passing through the origin, 45-degree line, moving like this. If you notice, what's going to happen is that this 45-degree line, this is a right angle triangle. This is a right angle triangle with exact same dimensions here. So it's an isosceles triangle here. It's an isosceles triangle here. Right angle triangle. And this is the hypotenuse. If you see, what's happening is that this line y equals to x is dividing these two lengths in equal portions, which basically means this point AB and this point BA exactly equidistant from this point y equals to x here, this point here and here, which happens when you get an image. If you take an image, when do we call that it's an image or reflection? When every point is giving you exactly the same distance from a particular line. It could be vertical line, it could be any line. Here in particular, this is happening with the line y equals to x. So therefore, and this is just an example, this is a random point a comma b. I took value so that you could understand it. You take any value which is on the graph, of course, which is on the graph, you will get the same relation. And that is why the graph of F inverse is essentially a reflection on y equals to x of F. It's just a reflection. It's like the mirror image of F, okay? Right opposite to y equals to x. So please write it down. If F has an inverse, then the graph of y equals to fx and y equals to f inverse x are reflections of one another about the line y equals to x. That is, each graph is the mirror image of the other with respect to y equals to x. That's going to happen. Let's take example here. Let's take the example. Suppose y is equal to 2x. Then first of all, x is equal to y by 2. So the invertible relation is that if y is equal to 2x, then x is equal to y by 2. In other words, we can just say that fx is equal to 2x and f inverse x. So now we have that invertible relation or invertible functional form is there. So we can say that f inverse x is nothing but x by 2. Okay, let's graph it. So this is the graph of y equals to 2x. In blue that you can see is the graph of y equals to 2x, because easily you can see that at 0 it's 0. At 1 you get the value 2, then at 2 you get the value 4, so on and so forth. Similarly, in purple you can see you have y equals to x by 2, the graph of x by 2. When x is 1, y is half, and so on and so forth, right? And in red, you can see it's the graph of y equals to x. Notice something. Any point on the graph that you will see, any point on the graph that you will see, if you will see the perpendicular distance, it's going to be the same on, from 2x and x by 2. Everywhere, which basically means it's nothing but a mirror image that you have. These two graphs are mirror image about y equals to x. Across y equals to x, they're exactly the same. Let's take another example. Let's take a non-linear example this time. Let me take two functions, x cube. If y is equal to x cube, x is clearly cube root of y, which means fx is equal to x cube is one function, and f inverse x is cube root of x. The functional form is cube root basically. So let's again have y equals to x as our basic line, and across this line, let's see if we are getting reflection or not. Let's create the graphs of y cube and cube root of x. This function that you can see, my friends, this is the graph of x cube. And here what you can see is the graph of cube root of x. The same thing out here. Okay, this is x cube and this is cube root of x. If you can notice, it's exactly the mirror image of each other. That's what happens with an inverse function. You get exactly the mirror image about y equals to x. Each point, the reversed point, they're like equidistant from y equals to x if you compare. Leaving you with the last example, and this is a homework for you guys. Try to graph both the functions on the same xy plane. Again, try to check whether they're reflections of each other. So y is equal to 1 by 3 of x squared plus 2. So x is equal to square root of 3y minus 2. I'm sure you can do that. From here, you can figure out it's 3y is equal to x squared plus 2. So 2 goes this side and you can take the square root. This is what you will get. So you can take f inverse x as square root of 3y minus 2. Next step, you prepare your xy plane, and in that you must have the line y equals to x. And now your task is, or your homework is, to construct both the curves fx and f inverse x and check for yourself, are they reflections of each other or not? Thank you very much.